talk real quickly about physical properties of alkenes and then start to get into reactions of alkenes. So physical properties first. So in general, they are considered non-polar, right? We just have carbon and hydrogen, and then they do have a double bond, so they're unsaturated, but they're still hydrocarbons. So just carbon-carbon and carbon-hydrogen bonds, those are all considered non-polar. So non-polar. So only London dispersion forces between one alkene and another alkene. So they're going to have relatively low melting points and boiling points. The melting point and boiling point do increase as the number of carbons increase. Remember, the more atoms you have, right, the more electrons you have, the stronger London dispersion forces are, right? You have more electrons moving, so stronger London dispersion forces as something gets bigger. So as the number of carbons increase, the melting point and boiling points also get larger. They are, for the most part, soluble in organic solvents, so things that are considered nonpolar, and then insoluble in water. So soluble in nonpolar solvents, insoluble in water. I did say soluble in organic solvents. A lot of times an organic solvent is like that term is used instead of non-polar solvents. I just use it out of habit. Sorry about that. Not all organic things are non-polar, right? So it's kind of a bad way to say it. It's how I learned it. So sometimes I'll do it that way. An alcohol is an organic solvent, but an alcohol is polar because it has that carbon bonded to oxygen and the oxygen bonded to hydrogen, right? Alcohols are polar. So when I say organic, I'm really talking about non-polar solvents, not all organic solvents. So in the world of solvents, if you see organic in front of it, they mean non-polar. Sorry about that if that's confusing. I know it's confusing. It confused me when I was learning it. So I don't mean to confuse you also. So we'll just say soluble in non-polar things because it's non-polar, right? Like dissolves like, and then insoluble in water because water is polar. There is an interesting difference being seen since cis and trans isomers. If I was to draw a cis version of 2-pentene and then our trans version of 2-pentene, there is actually a small dipole. There is considered, it's kind of weird because it's between carbon and carbon, but the carbons that have the double bonds are actually considered slightly more electronegative because of those pi electrons. So you can think of this as having a slight dipole, right? The net would be through the middle, where these ones, because it's symmetrical, they're going to cancel each other out. So this does have a small emphasis on small, but it does have a small net dipole. That doesn't really, it's not really enough to make it polar, but it does increase the boiling point compared to the trans version. So this increases the boiling point compared to trans. So we could say it's slightly polar. So I want to start talking about reactions next. I do have a reaction sheet posted on Canvas for chapter 10 also, just like we did with chapter 9. What I don't have on that sheet this time, however, is preparation of. So I'm going to add those first, and then just remember these aren't on the sheet. So you might want to add them yourself just so it's complete, or if you're making a handwritten list of reactions, make sure these get on there. So preparation of alkenes. And we've seen these before, which is why I didn't put them on the sheet when I originally made it, because there's nothing new here. These are all reactions we've seen before. So they're not unique, and that's why they didn't make the list, but I think they're worth mentioning. So our first one is just an E2, and then we're gonna have an E1. So just if I have an alkyl halide and we end up eliminating, so just a dehydrohalogenation of an alkyl halide, the easiest way is to actually do it with a strong base and do an E2 mechanism. So our first way, a dehydrohalogenation. So D means we're removing, and then hydro, a hydrogen, halogenation, a halogen. So we're removing HX. So dehydrohalogenation of our alkyl halide with a strong base. So I have an alkyl halide here. And then I'm just going to use hydroxide, but it could be a different strong base. And I'm going to end up removing my halogen and then a hydrogen on one of the beta carbons. So we can remove one from that carbon or this carbon. We actually would remove both, but the major product, the one we're going to get most of, is our more stable alkene, right? We are going to follow Zaysev's rule for this. So this is going to be an E2 mechanism. You still need to know it, so I could ask this mechanism. It's one that you've done a few times from chapter 8, so you still need to know it. An E2 mechanism, it does follow Zaysev's rule. So our major product is going to be the more substituted product, right? This is our major. We could get this also, but this would be our minor product. The second method we've also learned, this one's from chapter 9 from our alcohol chapter. So acid catalyzed dehydration of alcohols. So this one, we usually have a secondary or a tertiary alcohol. And then I use either sulfuric acid, H2SO4, or the TSOH version, right? And this is the one where when you do the mechanism, you could just use hydronium ions if you wanted. You don't need to, but I think it's a lot easier that way. And we end up removing water, so hydrogen from our beta carbon and the OH group. This one also follows Zaysev's rule. So my major product is going to be my more substituted product. This one was an E1 mechanism. We did the mechanism for this one in chapter 9. You still need to know it. This is the one, remember, hydroxyl groups are bad leaving groups, so we need to protonate that hydroxyl group first before we do the E2 mechanism. So E2 mechanism, make our OH group a better leaving group first. And again, it does follow Zaysev's rule. Our third way is also from chapter 9, and that's where if we have a primary alcohol, we use the POCl3 in pyridine. So primary alcohol. And I ended up, sorry, I flipped it upside down on you. Not that it matters, but sometimes it's harder to see what I'm doing if I do that. So we lost the hydroxyl group and then a hydrogen from here. So I had 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. I think I've said this probably a lot, but I'm really bad at losing carbons, so I always have to count them to make sure that I'm not losing carbons or gaining carbons or doing something weird with carbon. This was that E2 mechanism, but of course our hydroxyl group is a bad leaving group, so we need to make that better first, and that's where that POCl3 came in, right? One of those lone pairs on that oxygen attacked the phosphorus. We lost a chlorine. There was a few other steps in there, but we need to make that hydroxyl group a better leaving group first. And I would say it follows Hesov's rule, but I don't have any other options for this one, right? I only have one beta carbon, so that's the one we're going to lose. It's primary, so it's always going to be on N end. It doesn't have to be that end, but it'll always only have one carbon bonded to it, so it's only ever going to have one beta hydrogen. So those are our 3 methods. Again, all of them we've seen before, which is kind of nice when stuff doubles up. So far in this chapter, we already know 3 of our reactions, right? This was from chapter 8, and then chapter 9, that's a C, and then this was also chapter 9. So we're going to start talking about reactions of alkenes then. And the type of reactions that alkenes undergo are going to be addition reactions. Remember back when we were learning our 4 common types of reactions, addition is where we started out with a pi bond and then we ended up losing that pi bond, so we removed a pi bond. Essentially what's happening are those pi electrons are grabbing onto something. So the type of reactions we're going to look at are electrophilic, addition reactions. So our pi electrons are going to grab onto some sort of electrophile. So electrophilic addition reactions. So in general, I'm going to have my alkene. I'm going to add something to it. I'm just using XY, so our different reactions, there's going to be different things for those. Not X as in a halogen, just as in 2 things. Maybe that's a bad way to do it. Let's just do AB. And then we're going to end up with A bonded to one of those carbons that was involved in the pi bond, and then B bonded to the other. Remember, these are really just the opposite of elimination reactions, right? If I was to turn the arrow in the other direction, it's an elimination where we're making the pi bond. Addition reactions, we're getting rid of that pi bond. Generally, those 2 are going to be anti to each other, but we will look at specific mechanisms as we go through. So essentially my alkene is acting as my nucleophile. Remember, our electron sources were generally lone pair electrons or pi electrons. So since I have pi electrons, those are going to act as my nucleophile. And then either A or B is going to be electrophilic. So this will react with an electrophile. So the first one we're going to look at is a hydrohalogenation reaction. Not to be confused with the dehydrohalogenation reaction we just looked at, right? If we go back up here, one of the ways to make an alkene was a dehydrohalogenation, right? I'm removing a hydrogen and a halogen. This one is just a hydrohalogenation, so I'm adding a hydrogen and a halogen, so the opposite. I am going to make this unsymmetrical because we are going to have some regiochemistry that's important. So we're going to add HX, so a hydrogen and a halogen, and then my major product is actually going to have that halogen on the more substituted carbon. And if that carbon was chiral, we would actually get both stereoisomers. So we are going to go through a carbocation intermediate. It's going to be planar, so when my halogen adds, it can add from both sides. So we will get both stereoisomers. Also note I put the halogen on the more substituted carbon. So it follows what is called Markovnikov's rule. So we had Zaitsev's rule for going in the reverse direction, right? We want to form the more stable alkene. Markovnikov's rule is when we're going in this direction. And it's not specific just to these, but anytime we're going to go through a carbocation intermediate for addition reactions, it tells us that our major product is going to come from the more stable intermediate. So we're going to end up going through a carbocation intermediate, and I have options. I could have the positive charge on this carbon, and then I would have put the hydrogens here, or a hydrogen here. There's one to begin with, right? There was one there. Or I could have added a hydrogen to this carbon, and then my positive charge is here. Remember, the more substituted carbocations are more stable. So this is my more stable carbocation. So when my X minus adds, it's going to add to that one. So essentially the major product results from the more stable carbocation intermediate, which is the more substituted one, right? Tertiary carbocations are more stable than secondary carbocations. Kind of the shortcut way to do it is the halogen, so X in this case, will be on the more substituted carbon. And this might make more sense when we actually do the mechanisms. You can see how we're getting that carbocation, but we're going to get one. We want the more stable one, and then the halogen is going to add to where that carbocation is, right? To my non-octet carbon, it's missing electrons, so the halogen will add to that one, and that's going to be the more substituted one. So my halogen will be on the more substituted carbon. So this follows Markovnikov's rule. So we would say it's regiospecific. Right? It matters which region of the molecule you put that halogen on, right? This is my major product. We could get, I'm just going to draw it over here because I've run out of room. We could get this one. That's perfectly acceptable. We would have the plus minus version again if it was chiral, but this would be my minor product. Again, we don't just get the major, we just get most of it, right? That's why it's called major. So most of it looks like the one that I drew originally, where the halogen's on the more substituted carbon. So major, not only. So it is regiospecific. It's also, I guess I wouldn't say stereospecific because it doesn't matter. We get both stereoisomers if chiral, so not stereospecific. And then just watch out for rearrangements, because we are going to go through a carbocation. Run out of room, so watch for carbocation rearrangements. Anytime we have a carbocation, right, it wasn't just specific to chapters 7 and 8. Anytime we have a carbocation, if it can be more stable, it will rearrange to do that. Again, only if it makes it more stable, all right? Only if it makes sense to rearrange will it rearrange. So our mechanism, don't think I told you what X could be. X can be chlorine, bromine, or iodine. Sometimes chlorine isn't an option, so I want to try to remember to always tell you so you know. So our mechanism. Again, I'm going to make it unsymmetrical. Let's actually make it so we end up with something that's chiral. And then we'll use HBr. This is probably the polar mechanism that I used as my example when we were first learning mechanisms. So I have a partial positive hydrogen because it's bonded to that more electronegative bromine, right? The more polarizable bromine. I have pi electrons, so that's my nucleophile. That hydrogen is my electrophile, so it's going to grab onto that hydrogen. And then again, whenever we grab onto a hydrogen that's already bonded to something, we need to break that bond because hydrogen can only ever have one bond. So now I have options, right? I can put my hydrogen on this carbon, and then I have my positive charge on my tertiary carbon, or I can put my hydrogen on that carbon, and then my positive charge would be on the other carbon. We want our more stable intermediate, so I'm going to have this version. I'm actually making it so it's not chiral, am I? I'm going to go add another carbon. Sorry, guys. Stick another carbon on there. Right? That's going to be my more stable. My other option. Whoa. Is I could have this, right? That would be the intermediate that would give me my minor product. And if I said draw all possible products, then I'm looking for both. So do know that they're both possible. It's just the more stable one's going to be my major. So I have bromine floating around. Right, we broke the bond between hydrogen and bromine. So I have bromine, it has lone pairs, and it can attack that carbon. Since that carbon cation is sp2 hybridized, right? That carbon is planar, it can add from both sides. So I will draw them this time. I could have it where I just want to try to fit it. I guess we'll start up a little bit. I could have it where the methyl group is going out and that the bromine's going back, and then I can also have it where the bromine is coming out and the methyl group is going back, right? This is planar, right? sp2. So my halogen can add from both sides. Right, this less stable C plus would lead to the minor product. And I would still have both stereoisomers for it. The second type of electrophilic addition reaction we're going to cover is a halogenation. So the last one was a hydrohalogenation, right? We added hydrogen and a halogen across that double bond. This time I'm just going to add a halogen to both sides. So instead of HX, X2. And then our halogen is either going to be chlorine or bromine. And we're going to end up with, like I said, a halogen on both sides, but I do need to make sure that the two hydrogens are anti to each other. So if I want to put one halogen up, then the other needs to go down. And then I do need to fix the stereochemistry on these guys. There's a hydrogen there. And then this had this group. And then I did have that methyl group on it. So we do have anti-stereochemistry on this one. And that's a result of the mechanism. As we go through the mechanism, I'll talk about how it comes out to be anti. So anti-stereochemistry, if one halogen's up, the other's going to be down. If you wanted to have one coming out, then the other should be going back. That sort of thing. We don't generally think of chlorine, right? I have a bond between chlorine and chlorine or a bond between two bromines. We generally don't think of those as being polar, but bromine and chlorine are big enough that they are pretty polarizable. So they do have induced dipoles, temporary ones, but they do have them. So these guys have induced dipoles, right? They're pretty polarizable. They're relatively large with a lot of electrons, so it's easy to distort those electrons. So we can think of them as being polarized. Same with the chlorine. So one of the halogens in my diatomic halogen molecule is going to be electrophilic. So my mechanism, and because this is also an electrophilic addition reaction, right, my pi electrons are going to grab onto electrophile, which is why I wanted to show that there is induced dipoles on those, right? They are pretty polarizable. And I'm actually going to do this mechanism with an unsubstituted one first, just so you can kind of see where everything is going. It might be easier. The mechanism's a little weird compared to what we've done before. So remember, there are lone pairs on these. And then I also have the induced dipole. So I'm going to make that one partial positive and that one partial negative. So what happens is my pi electrons are going to grab onto the bromine because it's electrophilic, because of that induced dipole. But then the lone pair is going to go back and grab onto that other carbon. So if I just kind of as a side note, if I just grab the one bromine, right, and I didn't go back, I would like have a positive charge here. So once I grab, right, once the pi electrons grab onto the bromine, then that one carbon does become electron poor. So then the bromine's lone pairs are going to go back and grab onto that carbon. Bromine's going to have too many electrons then, so I'm then going to break this bond. Let me get this out of the way here. And then I'm going to draw those arrows again, just because it's a little unique and I think it's worth showing you again. So get my partial positive back on there. So pi electrons are going to grab onto a bromine. Lone pair is going to come back down and grab onto that other carbon. And then we're going to break that bond. You can draw that arrow up or you can draw it down. It doesn't really matter. But lone pair is going to go. So that actually should come from the pi electrons. And then that's actually going on to one of the carbons. I'm drawing it to that carbon, but it's symmetrical, so it doesn't really matter how I want to draw it. So what I end up with, and I'm going to draw, these are the two carbons that have the pi bond between them. And then that's where the pi electrons grabbed onto bromine. That's that bond. And then this bond is where the lone pair went back and grabbed onto the carbon. I still have two lone pairs on that, and if you do the formal charge calculation, there's going to be a positive charge. I have a methyl group, and then a hydrogen, and then another methyl group and a hydrogen. Because I drew my original trans, do make sure that your two methyl groups are opposite. So like this methyl group I have coming out, so then that one's going back, right? If I drew them cis, then I would have them both coming out or both going back. So make sure your stereochemistry of your intermediate here matches what we were given to begin with. So this is called a bromonium. Oh, can't write with my highlighter. This is a bromonium. Ion intermediate. If I used chlorine instead of bromine, it would be a chlormonium. ion intermediate. So either bromonium or chloromonium, kind of weird to say, depending on which one you have. And it is a bridge, right? I have the two bonds, so each carbon is bonded to that bromine. So I do have that second bromine floating around, and I'm going to squish it in here because I have everything. All the stuff I wrote is kind of in my way now. But that's going to attack one of those two carbons, and then I'm going to break one of the bridged bonds, one of the bonds to the bromonium intermediate. Because I have this thing blocking the top, right? The whole top part is blocked by this bridged bromine. It has to attack from the bottom. And this is how we're going to end up with our anti-stereochemistry. So let me get that highlight out of the way. So this is going to attack from down here. Then I'm going to break this bond. So again, because that bridged bromonium is blocking the top side, that second halogen needs to attack from the bottom. And let's go down here with it. So the two carbons that I was showing, this bromine I have up, right? I broke this bond. That's the one I broke. So this bond right here is this one that I just drew. This bromine that attacked from the bottom is going down, so these guys are anti to each other. I then have my hydrogen coming out, my CH3 group going back, my CH3 group coming out, and my hydrogen going back. So I'm going to redraw my bromonium intermediate because we could have actually done this one slightly different. So back to my bridged intermediate, and then I have on this side my methyl group coming out, hydrogen going back. On this side I had, right, if I go back and look, my hydrogen coming out and my methyl group going back. Sorry, that's really messy. So what I did the first time is I had my halogen attack my second carbon. This time I'm going to have it attack the other carbon. Because that can happen, right? I made this symmetrical, so there's nothing to force it to attack one side versus the other. So I'm going to have it attack that carbon, and then I'm going to break that bond. So I just redrew my intermediate, and then I had it attack my first carbon instead of my second, assuming the first is the one on the left. When I draw that product, this time I have bromine up on this carbon and down on this carbon. Hydrogen's still coming out over here. My methyl group is still going back. Here my methyl group is coming out and my hydrogen is going back. So, and it can do both of those with equal likelihood. So then the question is, from a stereochemistry standpoint, what is the relationship between those two? And by relationship, are they meso? Are they enantiomers? Are they diastereomers? Right? I do have two chiral centers, so what is our relationship between these two? Those are all going to be options. And I actually want to let you try to figure this one out on your own. Try rotating one of them, see if you can superimpose them, whatever your method is. So meso, enantiomers, diastereomers, what is our relationship between those guys? Our third type of electrophilic addition reaction is going to be halohydrin formation. And we talked about what a halohydrin was in the last chapter, right? That was a molecule where I have a halogen and a hydroxyl group on adjacent carbons, and then you can have other things on there. But on adjacent carbons, there's a halogen and then a hydroxyl group. And we use those as our starting point for making an epoxide, is how we use those. Right? We did an intramolecular SN2 reaction, right, where the electrons on my hydroxyl group attacked the partial positive carbon of my halogen, and then my leaving group left. So what we're doing here is we're making one of those. So making a halohydrin. So I'm going to start it with the same alkene. We're adding X2 again. This time my halogen is still either going to be chlorine or bromine. And then we're going to add water also. So the halogen that's on my halohydrin is coming from X2, I guess obviously, and then the OH group is going to come from water. My mechanism is going to be very similar to the mechanism we just did, except instead of having bromine attack that intermediate, we're actually going to have water attack that intermediate. So a very, very similar mechanism. This one is regiospecific, so I do want to put that hydroxyl group on the more substituted carbon. I didn't leave room for it. So my hydroxyl group goes on the more substituted carbon. So it is regiospecific. So halogen on less substituted carbon, hydroxyl group on more substituted carbon. We could say it follows Markovnikov's rule. Sometimes we'll call it the Markovnikov product. It doesn't really go through a carbocation intermediate, but the transition state would resemble one, if you want to kind of think about it that way. If not, this part here will help you. It also is stereospecific. And we're going to get that anti stereochemistry again. So this time the halogen and the hydroxyl group need to be anti to each other. So up here, I don't think I wrote stereospecific, anti-stereochemistry, so it is a stereospecific reaction, meaning it's only going to give one particular type. So anti, you're not going to get the syn version also. So the mechanism, like I said, it's very similar. So we'll use chlorine this time. And in the first part, it's exactly the same. So I have this induced dipole because chlorine's pretty polarizable. I do have these lone pairs on there. So my pi bond is going to grab onto the partial positive chlorine. A lone pair is going to come back down and grab onto that carbon, and we're going to break that bond. This time I'm going to get a chlormonium ion intermediate. So I'm going to focus on those carbons again. I'm going up to a bridged chlorine. It's two lone pairs and a formal positive charge. And then on this side I have two methyl groups, so one coming out and one going back. And then because this one's all symmetrical, it doesn't really matter how you want to do this one. I'm going to do the methyl group back and the hydrogen forward. Right? I don't have to worry about those two methyl groups on the left being, the same side or opposite sides to the other carbon because they're two of the same group. So that intermediate, what we would have done if we didn't have water is we would just have the chlorine attack. I'm actually going to have, we're using water. The way our book is doing the mechanism is it's using hydroxide then to attack instead of water, so it's deprotonating it. I'm going to do it with water because this doesn't make a lot of sense to me. I do have chlorine floating around, so I don't know if what they're doing is they're saying, okay, chlorine's going to take a proton, and then I'm going to end up with OH minus. But we know HCl is a strong acid. That reaction isn't necessarily in equilibrium. So I'm going to do it slightly different. I'm going to have it's slightly different than the book. I'm going to have water attack, and then we'll remove that proton after. You can use chlorine to remove it, which is, I guess, defeating the purpose of doing it this way. Or you can have another water molecule, which is how I'm going to do it, remove it. So, lone pairs, I'm going to attack the more substituted carbon, which is going to be this one on the left. Oop, the arrow got out of control. We're going to add onto that carbon, and then I'm going to break that bond. So those two carbons again I'm focused on. This time chlorine straight up on this side, and I have water here. It has a positive charge because it has 3 bonds and 1 lone pair if you do your formal charge calculation. Methyl group, hydrogen, and my methyl group. I'm then going to have another water. I learned it with chlorine, but again, that's defeating the purpose of why I'm just not using hydroxide in the first place. So one of those lone pairs is going to deprotonate this. That's a step we've done several times. So when all is said and done, chlorine, hydroxyl group, and you can draw it just straight up skeletal structures. I know I'm doing a weird combination where the methyl groups, I'm not drawing the carbon, but then the 2 carbons that have the halogen in the hydroxyl group bond, I'm actually drawing them out. You don't have to do it so weirdly. I just really want to kind of focus on the stereochemistry, and I think it's easier to see it this way when I actually draw out those carbons. So anti. So the halogen and the OH group, right, the hydroxyl group, are anti. Here we attacked the more substituted